Welcome back to part 2 of the video lecture for chapter 3. You'll recall in the first part of this video lecture, we talked about 3 of the 4 emergent or life-supporting properties of water. We talked about water having cohesive and adhesive behavior. We talked about water having a very good ability to moderate temperature. It takes a lot of energy to raise and lower the temperature of water, in other words. And we talked about the fact that ice is less dense than liquid water. So as a solid, water is less dense than its liquid form. So ice floats in water. And we talked about some of the ramifications of that. In the rest of this chapter, what we're going to talk about is the last property of water, or things related to it, and that is that water is an extremely good solvent. So water is often referred to as the solvent of life. So what's a solvent? Well, a solvent is anything that dissolves some other material. So let's back up for a second and think about a solution, right? A solution is a liquid that is a completely homogeneous mixture of other substances. The solvent of that solution is whatever is doing the dissolving. It's the dissolving agent, okay? So let's say you had salt water. You put solid salt into liquid water, the salt dissolves. In that case, you have a saltwater solution, a saline solution, and water is the solvent, okay? It's dissolving the salt. What do we then call the salt? It is called the solute. So whatever is being dissolved in the solvent is the solute, okay? So solvents dissolve solutes, and together they make up what's called a solution. Now, in particular, if we have a solution where water is the solvent, that is referred to as an aqueous solution, okay? SOLN is the abbreviation for solution. But this term aqueous implies, or suggests directly rather, that the solvent is water. And so when you think about the fluids in our bodies, in our cells, between our cells, whatever, those are all aqueous solutions, right? This is one of the reasons why we think of water as the biological medium, because it provides the environment in which our biochemistry occurs. The compounds, proteins, sugars, fats, nucleic acids, that kind of thing that make up the vast majority of our body mass have to interact with each other in a watery environment. Okay, the water allows them to float around, bump into each other, and when they bump into each other, we can get chemical reactions that produce the processes of life. So water then is the biological medium because it provides the medium in which those compounds can interact with one another. This is one of the reasons why it's so important for life, okay? All right, so let's talk about how it is that water actually dissolves so many things. Well, one of the primary reasons for this is the fact that water, as we've said, is a polar molecule. So the water molecule, again, I'll draw it here, okay, has a slight negative charge on the oxygen side and a slight positive on the hydrogens, and so it's polar as a result. That means that if there's another molecule or substance that has a negative charge on it, the positive hydrogen side of the water can attract to it. Opposites attract, right? If there's a molecule, let's say, or a compound that has a negative or positive charge on it rather, that's a charge that the negative oxygen side of water can attract to. So it's because water's polar and has opposite charges on either side of it that it can attract other molecules. And so when water dissolves something, what it's doing is being attracted to positive and or negative charges on that other substance. And so the water kind of coats that substance in what's called a hydration shell. Okay, think of this as a coating of water, so to speak, on a substance that's dissolved in water. So let's take a look. So let's imagine you put solid salt in water. Okay, initially you have a pile of salt in the bottom of this beaker of water. You probably know that you don't have to just stir that to make that salt dissolve. It will eventually dissolve on its own. If you stir it, it will dissolve faster. But what's going on here is that the water molecules, having positive and negative sides, will attract to the negative chlorine ions and the positive sodium ions in that crystal of salt. They will pluck those ions out and surround them. So look at chlorine, negatively charged, right? It's the positive hydrogen side of water that attracts to it and forms that hydration shell. Look at sodium, positively charged ion, a cation, right? It's the negative oxygen side of water that attracts to it, forming a hydration shell. So these two ions, sodium and chlorine, then are dissolved in water because they're coated in a hydration shell. Now, water can do this with other compounds as well. This sodium chloride that you see here in this figure is an example of an ionic compound. We talked about ionic bonds in chapter 2. But water can also dissolve compounds made of non-ionic polar molecules as well. So if I tell you a molecule other than water is polar, you should already know that that means that it has positive and negative charges on it, right? Even large polar molecules like proteins, for example, can dissolve in water if they have either ionic and or polar regions. So let's take a look. So here in purple, you see a large protein molecule. You're seeing the individual atoms that make up that molecule, and you can see that it's coated in a hydration shell of water. Why? We zoom in, you can see there are partial negative and partial positive charges on the surface of that protein, and every one of those is a place where a water molecule can either hydrogen bond or attract through opposite charge attraction or whatever. But the point is that we would say this protein is dissolved in water because it has a hydration shell around it. Okay, so a couple of definitions here, or terms that are going to be very important and that you're probably going to hear me say almost every lecture from here on out. And these relate to whether or not something will actually dissolve in water. So if I tell you that a substance is hydrophilic, okay, that tells you that substance will dissolve in water. So hydro, meaning water, and philic, meaning to love, okay? To love or to like or to attract to or to have an affinity for, an attraction to. Water loving is what this means, okay? Hydrophilic also means polar. So if I tell you a molecule is polar, you know it has positive and negative charges on it at least. That tells you there are places on it where water can attract, so water does. That means that substance will dissolve in water. It's therefore hydrophilic, water loving. Now, what about the opposite? Hydrophobic. A hydrophobic substance, again, water fearing, phobia, fearing, a hydrophobic substance will not dissolve in water. And so think about fat molecules, right? Oil. You put oil in water, it forms a layer that sits on top of that water, right? You can mix it up, but as soon as you stop mixing, it will settle right back out into separate layers. That's because the oil molecules, the fat molecules that they're made of, have no charges on them. They are non-polar molecules, no charges, and so there's no positive or negative charges for the water to attract to. So they repel water, and water repels them, okay? This is why oil does not mix in water. All right, that's very important when we start talking about cell membranes and how they're structured and keep their integrity a little bit later on. Okay, so keep these concepts here in mind. They're very important, all right? We're talking about water, though, here as a good solvent, okay? It dissolves a lot of things. It doesn't dissolve everything. It doesn't dissolve hydrophobic nonpolar molecules, but it does dissolve hydrophilic polar molecules. And as liquids go, or natural liquids go, it dissolves far more things than other natural liquids do. That's why it's a very good solvent. Okay, so still talking here about water's ability to dissolve things, right? That's the last emergent property of water we're going to talk about in this chapter. We need to kind of switch gears a little bit and talk about solute concentration in aqueous solutions. And the reason for this is because here in a little bit we're going to talk about pH and why that's so important, okay? So most chemical reactions occur in organisms, most chemical reactions in organisms involve solutes of one type or another that are dissolved in water. When carrying out experiments, we use the mass or the weight to calculate the number of solute molecules in an aqueous solution. So when we're talking about the number of solute molecules in a solution, ultimately we're talking about concentrations. Well, why do we care so much about concentrations of solutes in solutions? How abundant they are? We care because how concentrated a solute is has a direct impact on chemical reaction rates. So how fast chemical reactions proceed. Okay, so think of it this way. Let's say that you go to, you like to dance, you go to a dance bar, whatever, and you want to have a lot of room to dance around, and you don't like bumping into other people. Imagine that bumping into somebody else would be akin to a chemical reaction. So maybe you go to a bar on Friday night at 6 o'clock and you want to dance. There probably aren't going to be a lot of people there at that time of day on a Friday, so you maybe have the dance floor, you and your partner have it to yourself. So you don't bump into anybody. There's a low concentration of humans on the dance floor, so they're not bumping into each other, so you have a low rate of chemical reaction. Now, what if you go to the same dance floor at, say, 11 p.m. on a Saturday night? Well, now the place is packed. And so you go out on the dance floor and there are people everywhere and you're dancing, but you're constantly bumping into people. So the number of humans is highly concentrated on the dance floor and there are lots of people bumping into each other, lots of chemical reactions as a result. When molecules are highly concentrated, they will bump into each other more often and therefore you have more chemical reactions. So that's why it's important to understand or know what the concentration of solutes is if you're trying to understand why a chemical reaction is proceeding at the rate at which it is. And in cell chemistry, which is what this course is mostly about, we are trying to understand how cells operate, and you cannot do that without understanding chemical reactions and their rates. All right, so as I said, when we're carrying out experiments, we use the mass to calculate the number of solute molecules in an aqueous solution. All right, so a couple of ways to talk about this. First of all, we have what's called molecular mass. All right, molecular mass is simply the sum of all the masses of all the atoms in a molecule. So for example, let's say I want to know how much a molecule of glucose weighs. Glucose is a simple sugar, C6H12O6. That molecule as a whole has a certain amount of weight to it, mass to it. If I know the weight of carbon, the weight of hydrogen, and the weight of oxygen, which I can get from the periodic table, I can add them all up, right? 6 times the weight of carbon plus 12 times the weight of hydrogen plus 6 times the weight of oxygen will give me the molecular mass of glucose, all right? Now, we can convert that directly into concentration, okay? Now, numbers of molecules are usually measured in terms of moles. This is not a furry little burrowing animal, okay? A mole is an absolute number of atoms or molecules or whatever. All right, 1 mole equals 6.02 times 10 to the 23rd. So let's say, for example, you have a mole of glucose. That means you have 6.02 times 10 to the 23rd copies of glucose. So take that decimal that you see right there and move it 23 places to the right. In other words, take it out of scientific notation. You realize that's a really big number. A million is 6 decimal places. A billion is 9. A trillion is 12. This is 23. That's a huge number, okay? So if we had a pile of carbon and I told on a table and I told you that was 1 mole precisely, you would know there would be 6.02 times 10 to the 23rd copies of carbon in that of carbon atoms in that pile. And if you know the weight of each carbon atom, then you know the weight of 1 mole of carbon, right? Okay. Now, another way to think about this is in terms of what's called molarity. Molarity is the number of moles of a solute per liter of a solution. Okay, by the way, we abbreviate that capital M. Molarity, again, is the number of moles of solute per liter of solution. So let's say we have a 2 molar solution of sodium chloride. this means there are 2 moles of NaCl in 1 liter of salt solution. Okay, so you have 1 liter of salt solution. How concentrated is it? There are 2 moles of NaCl in that. A 5 molar solution, 5 moles of NaCl, and so on. The point is that if I know how much 1 mole of NaCl weighs, and I want to make a 2 molar solution, I simply double that weight, or pull out that much NaCl from the container, put it in a beaker, fill it to 1 liter, and now I have 2 moles, a 2 molar solution. Okay, so in this way, we can convert the weight of something directly into concentration, and vice versa. All right, so why do we care about all that? We care because we want to consider pH. All right, so if you're not aware, the average pH of human blood is about 7.3. 7.3 is slightly on the basic side of things. Think about the acid-base scale, right? The pH scale. You go from 0, which is highly acidic, all the way up to 14, which is highly basic. 7 is neutral, right in the middle. It's not an acid or a base. pH of blood is about 7.3. It's slightly on the basic side. Okay, and our bodies have to maintain that particular pH. If pH goes out of whack, if it goes much above 7.4, 7.5, or much below 7.1, then all kinds of bad things start to happen. Generally, reaction rates either speed up or slow down. So pH directly affects chemistry, cell chemistry. If pH gets too far out of whack, it can actually cause cells to die, which is not a good thing. So we need to understand something about pH, but keep in mind that an understanding of pH involves an understanding of concentrations. That's why we're talking about all this stuff before, right, with regard to molarity and all that. Okay, so what is pH? Well, pH is a phenomenon that relates to the sort of strange behavior of the water molecule, okay? Water molecules go through a reaction called dissociation. It's a dissociation reaction. And what happens is that you'll have 2 water molecules. Let's say you have pure water, so a container of pure water. 2 water molecules will react with each other. And what happens is that a hydrogen, let's say from this water, will split off and attach itself to this water molecule. Now, when it does that, this oxygen, being electronegative and sharing an electron with that hydrogen, will steal that hydrogen's electron. So when the hydrogen breaks away and goes over here, it does so as H+. Remember, hydrogen only has 1 proton and 1 electron. So when it splits off the water and the oxygen steals that hydrogen's electron, it's nothing more than a proton, H+. So what you end up with is H+ plus H3O. OH minus. Okay. Now, why do I say that? Well, what I should have done is actually said this is not H+, it's the H3O+. Okay. If you take 1 hydrogen and attach it over here, you have H3O. But because that hydrogen is just a proton, H3O plus is what you get. This is how, let me just show you with this figure here. It's the same thing. Here we have 2 water molecules, H2O, H2O, okay? They go through a dissociation reaction. This one loses a hydrogen, comes off and attaches over here. Now we have H3O plus, right? This is what I also called H plus in the previous slide. H3O plus, or what's known as a hydronium ion, is how chemists refer to this. Biologists just simplify it and call this whole thing a proton, okay? So technically this is hydronium ion, H3O plus. What you're left with over here on the water that lost the hydrogen is hydroxide, OH minus. Hydroxide ion, OH minus. Why the minus? Because the oxygen stole the electron of the hydrogen that it lost. Okay, so we have H plus and OH minus. All right. Now, this reaction, excuse me, is reversible. which means it can go right back the other way. Notice how the arrows go both ways here, right? So this hydrogen can come back off, reattach to the water, and you go right back to two water molecules. Now, normally, this is happening all the time in pure water. The thing is that the hydronium ion, or proton, is acidic, okay? Hydroxide is basic. As long as the concentration of these two ions, hydronium and hydroxide, or proton and hydroxide, are equal, then you have a pH of 7. You have the same number of acidic ions as you do basic ions, and so the pH is 7, it's neutral, okay? So, if they're equal, it's neutral. It's when, excuse me, it's when the concentration of these two gets out of balance that our pH changes. If proton, this one here, increases in concentration while hydroxide decreases, because proton is acidic, that will drive our pH number down below 7 into the acidic side of things. Vice versa. If hydroxide increases in concentration and proton goes down in concentration, this will drive our pH up to the basic side of things because hydroxide is basic. So pH, the pH number that you get when you take the pH of a water sample or whatever, is telling us the relative concentration of these two ions. In particular, it's telling us the concentration of proton, hydronium ion. That's what the pH number is. It's telling you the concentration of proton, and from that, you can infer the concentration of hydroxide. Okay, so changes in concentrations of proton and hydroxide can drastically affect the chemistry of a cell. As I said, the concentrations of these two ions are equal in pure water. But if we add an acid, let's say, or a base to that pure water, we can alter the concentration of these two and either convert that solution into an acid or a base, depending on which way the pH goes. So we use the pH scale then to describe whether a solution is acidic or basic. All right, so let's define an acid. An acid is any substance that increases the proton concentration of a solution. Good examples of acids: hydrochloric acid, HCl. If you put hydrochloric acid in water, the hydrogen and the chlorine separate from each other. The chlorine, just like oxygen, steals the hydrogen's electron, and what you end up with is a source of H+. It increases in concentration, therefore adding HCl drives the pH down. Now, a base. Sodium hydroxide is a good example of that. Both of these are very commonly used in chemistry labs. So let's say you add sodium hydroxide to water. The hydroxide, OH, splits away from the sodium. Sodium keeps or takes on a positive charge. The OH takes on a negative charge, so you get a source of hydroxide. Right there, they dissociate. Adding sodium hydroxide increases the concentration of hydroxide, and basically it will drive the pH above 8, okay, or above 7 rather. So it goes on to the basic side of things. So a base is any substance that reduces the proton concentration. Now that's a little bit different than what I just defined, but imagine that you add sodium hydroxide to a solution or to water, and these two split or separate, okay? This becomes hydroxide, OH negative, which can then recombine with proton and be converted to water. So if you add hydroxide by adding a base, you're adding something that mops up proton, takes it out of solution. If proton's acidic and the base is driving down the concentration of proton in that way, then it will drive the pH up above 7. So a base is any substance that reduces the proton concentration in that way. An acid is any substance that increases the proton concentration. All right. So let's talk about the pH scale a little bit. So as I said, our pH scale goes from 0 to 14. Okay. So in any aqueous solution, water-based solution, at 25 degrees Celsius, which is standard room temperature, the product of the proton concentration And the hydroxide concentration is constant, and it can be written the following way. So when we put brackets around something in chemistry or biochemistry, that just means concentration of whatever is inside the bracket. So this means concentration of proton. If we multiply concentration of proton by the concentration of hydroxide in any aqueous solution, we always get the same answer. The concentration is 10 to the minus 14th. Okay, well, you might be thinking, well, how is it that the concentrations can differ, but you always get the same answer when you multiply them together? The answer is that because these two have to equal up 10 to the minus 14th, if the concentration of proton goes up by a certain amount, concentration of hydroxide has to go down by the same amount. That's the only way you always get this as the same answer. If one goes up, one goes down, all right? So how do we then define pH? Well, pH equals the negative logarithm of the proton concentration. Don't worry about logarithms if you don't know how to do them. It's not a big deal. Okay, this is a real simple calculation here. So again, pH is simply a measure of proton concentration. What measure? It's the negative logarithm of the proton concentration. So let's say we have a neutral aqueous solution. So our pH in that case is 7, all right? In that case, we know that our proton concentration equals 10 to the minus 7th, all right? So if you take the negative log of 10 to the minus 7th, okay, so pH equals the negative log of 10 to the minus 7th, you get 7. In other words, if you're trying to find the pH number and I give you a concentration, the pH number is the same as the exponent. It's the absolute value of the exponent. So if your proton concentration in a solution is 10 to the minus 7th, you could plug it in the calculator and take the negative logarithm of it, but it's going to spit out the number 7.0. What if your proton concentration equals 10 to the minus 5th? Your pH then equals 5.0. All right. Now remember, I said that your proton concentration multiplied by hydroxide concentration has to equal 10 to the minus 14th, right? So when you multiply numbers that are exponents, what are you really doing to the exponents? You're adding them. That's the way this works, okay? So if we have proton concentration of 10 to the minus 7th, and we have hydroxide concentration of 10 to the minus 7th, multiply them, and you get 10 to the minus 14th. What if your proton concentration goes down to 10 to the minus 8th? You understand, in the scientific notation, that's a smaller number than that one is. It's further away from 0, right? Okay. Proton concentration goes down to 10 to the minus 8th. What has to happen to your hydroxide concentration in order for them to be multiplied together to equal 10 to the minus 14th? It must go up to 10 to the minus 6th. All right? So, if you know what your proton concentration is, you can figure out what your hydroxide concentration is. But the pH of the solution is always going to be the exponent on the proton concentration. So this is going to be a pH of 10 to the minus 8th. I'm sorry, a pH of 8. And that's basic, right? Why is it basic? Because you have a higher concentration of hydroxide. So this is OH minus, and that is H plus. Higher concentration of hydroxide, lower concentration of proton. You got more of these and you got these. That's why our solution is basic. How basic is it? pH 8. See how that works? It's pretty straightforward, okay? All right, so let's look at our pH scale then. So here we have in the middle pure water pH 7. Let's go on the basic side first, okay? So first of all, notice that in your little beaker over here, this is showing you the same concentration or number of hydroxide ions as protons. So proton equals hydroxide, pH 7. Now, as we go this way, hydroxide begins to outnumber proton. Hydroxide being basic, that drives your pH number up to the basic side of things. Human blood, 7.3. Tears, about the same. Seawater, about 8. Milk of magnesia, right? You take that for acid stomach because it neutralizes the acid. Why? it's a strong base, 10.5 or so. Household bleach, oven cleaner, very, very basic. These can give you what's called a caustic burn. Okay, it's similar to an acidic burn, but it's a different thing. It's a burn, tissue damage, but it's a result of extreme high pH, basic pH. Now let's go below 7. Saliva, slightly acidic, 6.5, something like that. That's what helps start to break down your food in your mouth as you're chewing. Urine, pH 6, black coffee 5, vinegar, you know, obviously is very acidic, but so are soda drinks, for example, that can dissolve teeth, for example. Battery acid, gastric juice, extremely acidic. These can give you a nasty acidic burn, but notice here, much higher concentration of proton than hydroxide. So again, pH then is just a measure of the relative concentration of these two ions. These two ions that are a result of dissociation in water, all right? And pH is very important because too high or too low of pH can affect chemical reaction rates in our bodies, which can result in really bad outcomes. So, because we need to maintain a relatively constant pH in our body fluids of around 7.3, our bodies have systems called buffers, okay? Chemical buffer systems that are essentially a way for our body to maintain constant internal pH. So the way these things work is that they are compounds and they can reversibly combine with either proton or hydroxide. So let's say, for example, we have a situation where our pH in our blood is going acidic. So maybe it's dropping below 7 and going down to 6.9, 6.8, something like that. That can kill pretty quickly, so our bodies need to counteract that. What our bodies will do in that case is they'll have chemical compounds in our bloodstream that will release hydroxide, OH minus. Well, think about it. Why is the blood going acidic? Because proton, H plus, is building up in solution. You want to get that out of solution. How do you do it? Your buffer systems release hydroxide, OH minus. OH minus binds with H plus proton, and you get water, right? So the buffer then is mopping up the extra proton. Let's say the reverse is true. Let's say you've got a situation where your blood is going basic. Maybe it's going 7.4, 7.5, 7.6, something like that. In that case, your proton concentration is too low, your hydroxide concentration is too high. Basically, your buffer systems can release extra proton into your bloodstream, which will bind with the excess hydroxide, convert it back to water, and bring your pH back down. There are various different types of these buffer systems in our bodies, and they act automatically. We don't have to think about it. We have systems in our bodies that monitor our pH, our blood pH, our tissue fluids pH values, and they automatically release these buffers to bring or keep that pH at a normal level. And it happens automatically as part of what's called physiology, right? Physiology is the combined total of how our bodies maintain constant internal environment, pH, temperature, that sort of thing. So this happens automatically without you knowing it, but it's a result of chemical buffer systems in our bodies, okay? All right, well that wraps up the video lecture for Chapter 3 then. The next one will be Chapter 4 on introductory organic chemistry. So we'll talk about organic compounds, how they're structured, what their shapes are like, that kind of thing. Fairly short chapter, but we'll get to that in a little bit.